Look at a modern building with a complex, sculptural facade, with deep shadows, sharp angles, and seemingly impossible thin profiles. Now, tap on that surface. It's not stone, and it's not traditional heavy precast concrete. What you're likely seeing and hearing is the work of a modern engineering marvel, Glassfibre Reinforced Concrete, or GRC. For decades, architects designing complex forms faced a brutal choice: use heavy and expensive precast concrete, which requires a massive supporting structure, or use less durable materials that couldn't handle the elements. GRC shattered that compromise. It gives us the strength and mineral feel of concrete, but at a fraction of the weight, allowing for breathtaking designs that were previously unbuildable or unaffordable. But what exactly is GRC? How is it made? And what are the critical secrets to designing and detailing a GRC facade that will last for decades without failing? We're peeling back the layers on one of the most transformative materials in modern architecture. Let's start with the basics. What is GRC and how is it different from traditional concrete? At its core, GRC is a composite material. It consists of a high-strength, durable cementitious matrix, but instead of using coarse aggregate and steel rebar for reinforcement, it uses fine aggregates and millions of specially formulated alkali-resistant or glass fibers. These fibers are dispersed throughout the mix, and this is the key. They act as the primary reinforcement, controlling cracking and providing tremendous flexural and tensile strength. The manufacturing process is where the magic happens. The most common method is spray-up, where a stream of the cement slurry and a stream of chopped glass fibers are simultaneously sprayed into a mold. This creates a highly consistent, high fiber content panel. This process allows for incredibly thin sections, as slim as 10 millimeters, whereas traditional precast would need to be 10 times thicker to achieve similar strength-to-weight performance. This radical weight reduction, often up to 80% lighter than precast, is the single biggest game changer. So, why would you specify GRC over other materials like precast concrete, aluminum composite panels, or even GFRC's cousin, UHPC? The advantages are numerous and significant. First and foremost is the weight, which translates directly to cost savings on the primary building structure, smaller foundations, and faster, cheaper installation with smaller cranes. Second is its phenomenal flexibility in form. GRC can be molded into virtually any shape, from sharp, parametric folds to smooth, double-curved surfaces, capturing the architect's intent with incredible fidelity. Third is its durability. It's non-combustible, has excellent impact resistance, and it's impervious to rot, rust, and UV degradation, but a major advantage over aluminum panels is its thermal performance and lack of thermal movement. GRC has a coefficient of thermal expansion much closer to concrete and masonry, meaning expansion joints can be spaced further apart than with metal panels, which expand and contract significantly with temperature changes. A common drafting mistake to avoid is copying aluminum panel joint details directly onto a GRC project. You'll end up with over-designed and unnecessarily complex joints. Now, let's get into the nitty-gritty of designing a GRC facade. This is where your detailing makes or breaks the project. The first critical decision is the panel system. Will it be a single skin, a sandwich panel with insulation, or a rain screen? Connections must be designed to resist gravity loads, wind suction and pressure, seismic forces, and accommodate tolerances and thermal movement. The gold standard is a 4-point connection system, typically using stainless steel cast-in anchors within the GRC panel that connect to adjustable brackets on the building structure. Why 4 points? It creates a statically determinate system, meaning the load paths are clear and predictable, and it prevents the panel from being overconstrained, which could lead to cracking from minor structural movements. A massive workflow secret is to use BIM software like Revit to model not just the panels, but the connection brackets and shims in 3D. This allows for precise coordination with the backing structure and enables the creation of detailed installation drawings that show the installers exactly how to adjust for perfect alignment. Finally, let's talk about the digital workflow and common pitfalls. Designing a GRC facade is a highly collaborative process between the architect, the structural engineer, and the GRC manufacturer. The process starts with a 3D model from the architect, often from Rhino for complex forms. This model is then taken by the GRC specialist and panelized, meaning they divide the large surface into manufacturable and transportable panels. This is where parametric tools like Glassfibre are invaluable, as they can automate the division, optimize for joint alignment and panel repetition, and even generate the unique fabrication data for each panel, accounting for draft angles and demolding. It combines the aesthetic versatility of concrete with a lightweight, high-strength profile that makes ambitious designs structurally and economically feasible. By understanding its material properties, mastering the details of panelization and connections, and integrating the manufacturer early in the digital workflow, you can harness the full power of GRC to create durable, beautiful, and high-performing building facades. The connection design, in particular, is a critical life safety element and must be calculated by a structural engineer for the specific project, considering local wind, seismic, and building code requirements. If you found this deep dive into GRC facades valuable and want to see a follow-up video on how we model and detail a complex GRC panel connection in Revit, make sure to subscribe and hit the bell icon. Let us know in the comments what other building materials you'd like us to explore next.